In this section, we will talk about the ideal gas law, which is kind of the overall gas law that all the others can be derived from. So we looked at these different relationships between volume and pressure, volume and temperature, volume and trains, volume and moles of gas and trains. And so we can combine those laws. I think most 1A students are not interested in how that happens, so I won't even talk about it. But what we end up with is PIV-NERT, the ideal gas law, PV equals nRT. So here we've got pressure times volume is equal to the moles of gas times a constant R times the temperature in kelvins. And R is called the ideal gas constant, and we will most frequently use R as 0.08206, and these units are kind of funky, liter atmospheres per mole Kelvin. These are the units that are needed in the other variables. So the volume needs to be in liters, the pressure in atmospheres, amount in moles, and temperature in kelvins. That's the ideal gas constant. This is a table showing you the relationships between these different laws. And what I'd like to show you now is how you can get any gas law you need from the ideal gas law. So we can write the ideal gas law with subscripts of 1. R is a constant, so it doesn't have any subscripts. And then we can divide by the ideal gas law with subscripts of 2. At condition 1, PV equals nRT. At condition 2, PV equals nRT. And so if I divide this side by PV and this side by nRT, I still have an equality. Now what we can do is we'll just cancel out anything that doesn't change. The ideal gas constant doesn't change. So R divided by R is going to cancel out. So let's say that we had a question where volume and moles of gas were changing, pressure and temperature were not changing. So if the pressure isn't changing, sometimes they tell you what the pressure is, other times they don't. But if it's constant, then you know that pressure 1 is equal to pressure 2. So the pressures are going to cancel out. If the temperature isn't changing, the temperatures will cancel out. So what am I left with then? V1 over V2 equals N1 over N2. We can write that rearranged a little differently. And that's Avogadro's law. We can get Charles' law and Boyle's law the same way. So I would encourage you to do that. There's at least one question on the worksheet that uses what's known as the combined gas law that we don't really talk about, where you've got more than 2 things changing. And so in order to get the equation for that, there's another one where they put 2, all of these were volume and something. There's another problem where I think it's temperature and pressure are changing, and there's no equation in the book for that. This is how you find an equation that you need. Okay, any questions? It's completely okay that this doesn't look exactly like how we were given Avogadro's law, because if we use this equation, we're going to come up with the same answer anyway. So let's practice using the ideal gas law. An 8.50 liter tires contains 0.552 moles of gas at a temperature of 305 Kelvin. What is the pressure in atmosphere and PSI of the gas in the tire? So we can apply our same problem-solving strategies. We read the entire question, we highlight the numbers with their units, and then we identify what am I trying to find pressure in atmospheres and PSI. Do we have things changing in this problem? We talk about heating up or adding gas. No, nothing's changing. That's a big clue that we need to use the ideal gas law. Of course, the title up here kind of gives that away, doesn't it? Sometimes you read a question like this and there's so many words that you're like, well, I don't know if things are changing or not. It's just a big mess. Well, you can make a table like we did with the other ones, labeling everything ones and twos and putting them in columns. If it's an ideal gas law problem, you'll just end up with one row. And you'll have everything labeled and you won't have wasted your time. But here we're going to, recognize, okay, this is an ideal gas law problem. So let's record these different numbers and identify what variable they are. So 8.50 liters, is that P, V, N, or T? That's V for volume, right? It doesn't say volume, but we know that liter is a unit of volume. And then here we have 0.552 moles. What letter is that? N. And then we have 305 Kelvin. And this one, they actually tell us this is the temperature. But again, we should recognize that it's the temperature from the unit. So that's T. And then what are we trying to find? P. Trying to find P. So nothing's changing. This is going to be a PV equals nRT problem. So what am I trying to find? I'm trying to find the pressure. So I'm going to rearrange this equation to get pressure by itself. I'm going to divide this side by volume so the volumes cancel out. And I'm going to divide the other side by volume. So pressure is equal to, nRT divided by V. Well, there's an R in there, and we didn't write down what that was. So let's add that in down here. I do give you this number on the info sheet for the exams. You'll be able to do problems a lot faster if you memorize it. 0.08206. And the units are liter atmospheres per mole Kelvin. So this is telling us what our other units have to be. Let's look at these units and see if they match up. Are these all the correct units? Yeah, they are. We've got liters, moles, and Kelvin. There's liters, moles, and Kelvin. So sometimes we have to do some unit converting before we can put the numbers into the ideal gas law. So now I'm going to just plug everything in. N is 0.552 moles. Always write the units. R 0.8206. Write all these stupid units. Liter atmospheres per mole Kelvin. And the temperature was 305 Kelvin. And then all of that is divided by volume, 8.50 liters. Always good to check the units before you put the numbers into the calculator. And if we look at these units, we see that a lot of them cancel out. Liters will cancel, moles will cancel, kelvins will cancel. And the unit that is left is atmospheres. So then the pressure will equal 0.552 times 0.08206 times 305 divided by 8.5. I'm getting 1.62 unit would be atmospheres, and all of these numbers that we were using here had 3 sig figs except for R. So our answer should have 3 sig figs. So we're supposed to report the pressure in atmospheres and in PSI. How do we convert from atmospheres to PSI? We look up the relationship in the table, right? I don't expect you to memorize this one. 1 atmosphere is equivalent to 14.7 PSI. So that's 23.893 PSI. I'm using these extra digits until I'm all done, and then I'm going to write my rounded answers. So 1.63 atmospheres, 23.9 PSI. Any questions? It's important to have the units straight. If the units are wrong, the answer is going to be wrong. Let's do another one. What volume does 0.556 moles of gas occupy at a pressure of 715 millimeters of mercury and a temperature of 58 degrees Celsius? Well, again, we read the question, we highlight the numbers. And then I'm going to highlight the question. What volume? Now I'm going to take those numbers with their units and write them down. 0.556 moles, 715 millimeters of mercury, 58 degrees Celsius. So what is the variable, the letter for amount in moles? It's N. And this is the pressure, millimeters of mercury, so that's going to be capital P. And this is a temperature. And we are trying to find the volume. So again, nothing's changing like we had in our previous problems where things were heating up and expanding and stuff like that. So we've got PV equals nRT. This time we're solving for the volume. So rearrange the equation first, and then write out the rearranged equation. V equals nRT divided by the pressure. So we need R again. Let's put that in here. 0.08206 liter atmospheres per mole Kelvin. The units in the ideal gas constant tell me what units I have to use for my other things. N in moles, is that good? Pressure in millimeters of mercury, is that okay? No, it's not. It needs to be in atmospheres. So I need to convert to atmospheres. 1 atmosphere is 760 millimeters of mercury. I'm going to sneak that in down here. Hopefully that's not confusing. 715 divided by 760. 0.940. This should have 3 sig figs. 79 atmospheres. So that's my pressure in atmospheres right there. What unit do we need on the temperature? Kelvin. So to convert Celsius to Kelvin, I'm going to add 273. So 58 plus 273 is 331 K. Okay? Let's just maybe have a dividing line in here so things don't run into each other. Okay, so now I've got all the units correct, so I can put my numbers in. 0.556 moles. R is 0.08206. Here, atmospheres per mole Kelvin. And then barely enough room for my temperature over here, 331 K. Divided by the pressure, 0.94079 atmospheres. So again, my units are going to work out. Moles are going to cancel, atmospheres are going to cancel, kelvins are going to cancel. I did that wrong. Let's try that again. Moles cancel moles, not atmospheres. Atmospheres cancel atmospheres, and Kelvin cancel Kelvin. That's better. Okay, so my volume then, 0.556 times 0.08206 times 331 divided by 0.94079. $16.052, and the unit is the one that's left in my equation here, which is liters. And so I'm going to round this to 3 sig figs. I'm going to get 16.1 liters. Now, if you are on good terms with your calculator, you know that you can store constants in your calculator. Some calculators have a whole bunch of constants already stored in there for you. Others, you can do like 3 or 4 and you have to put them in yourself. If you're that kind of person, you can definitely store the ideal gas constant as one of those values, and instead of typing it in every time, you can just retrieve it. That's not cheating. Okay, it's not cheating. Any questions? $16.1 liters. Another one. Yeah, question.
So, it's just about sig figs. So
Mhm.
when this is
That's an excellent question.
Kelvin, why doesn't it have 2 sig figs?
That's a great question. So looking at this temperature, when this gets converted to Kelvin, how come it ends up with 3 sig figs instead of just 2? It's because we're adding, not multiplying.
So is it just because the 3 sig figs is like the least amount of precision, or the 3?
Well, so the rule for adding is fewest number of decimal places, right? So this has 0 decimal places. It ends in the ones place. And what we're adding also ends in the ones place, or it could have 2 decimal places if we use the more precise value. But our initial temperature is what's going to limit things. So our converted temperature will also end in the ones place. So you'll often see that you increase the number of sig figs when you turn your temperature from Celsius to Kelvin. And that's okay. The rule for temperature is just keep the same decimal places, right? So if your temperature you start with ends in the ones place, in Kelvin it should also end in the ones place. In Fahrenheit it should also end in the ones place. Yeah, good question. Anybody else? Determine the pressure in millimeters of mercury. of a 0.133 gram sample of helium gas in a 648 milliliter container at 32 degrees Celsius. So these are all using the same equation, but they're getting a little bit more complicated because the first one, they just gave us all the numbers with the correct units, right? And in the second one, we had to convert a couple things. And then in this one, we're going to have to do a little bit more. But again, let's highlight the numbers. 0.133 grams, 648 milliliters, 32 degrees Celsius. Trying to find pressure in millimeters of mercury. So I've got 0.133 grams. I have 648 milliliters, and I have 32 degrees Celsius. So milliliters, that's the volume. Degrees Celsius is the temperature. The mass. Well, N stands for amount of gas. The correct units are moles of gas. Here we're given grams. But we can change grams into moles. So this is where we're going to get our N from. How do we change grams of helium into moles of helium? We're going to need the molar mass. So I have grams here. I'm trying to get to moles. So grams to moles on the top. And then this gram comes down here, so I can get rid of it. So I put the units in like that. And that's going to tell me where to put my number. I find the number on the periodic table. The molar mass of helium is 4.003. Always good to check that. 4.003 grams is 1 mole. 0.11, nope, not 0.113. 0.133 divided by 4.003. 0.0332. We want to keep 3 sig figs. 25 moles. So we're going to be looking for pressure, and we're also going to be using, again, the ideal gas constant. Which, I mean, this is like its own cheat sheet, right? It tells you what the units need to be. So my volume in milliliters, that's not going to work. I need to change that into liters. So I want milliliters to go to liters, and I'll have milliliters on the bottom, so those cancel out. And then I recognize that milli stands for times 10 to the minus 3. So 1 milliliter is 1 times 10 to the minus 3 liters. And I'm going to get 0.648 liters. There are other ways that you might do that conversion. You should always make sure that it's reasonable. So I think we can all recognize that a milliliter is smaller than a liter, right? Because you can picture a 10 mil graduated cylinder, and a milliliter is 1/10 of that. And we all know how big 2 liters is, right? It's a bottle of soda. Right, so a liter is much bigger than a milliliter. If we have a small unit, the small unit's going to have the bigger number. The big unit is going to have the smaller number. So that's one way that you can make sure that you did that, because it's very common for people to move the decimal point in the wrong direction and end up with 648,000 liters. So temperature to Kelvin, again, we'll add 273. I think that's 305. Our temperature ended in the ones place. When we convert it, it still ends in the ones place. PV equals nRT. We're solving for pressure again. So divide by volume. Pressure is nRT over V. Let's see if I can get it to fit in here. 0.03325 moles. No, I don't think it's going to work. I'm just going to go to the next line. 0.033225 moles. And there's R. And Kelvin. Just snuck it in there. Dividing by the volume in liters. Double checking our units. Moles cancel, moles cancel moles, liters cancel, kelvins cancel. .2833 atmospheres. Is that the correct answer? No, we found the pressure, but it's not in the unit that they asked for. It's in atmospheres. So we're going to have to convert this to millimeters of mercury. Atmospheres down here. All the pressure conversions can be done in one step. So 760 millimeters of mercury is 1 atmosphere. So I multiply by 760. And I get my pressure as 975.29 millimeters of mercury. And I'll round that to 3 significant figures, 975. Any questions? So when we're doing gas law problems, you're going to need a gas equation, either one of the simple gas laws or the ideal gas law. You're going to need an equation. You sometimes also will need to do some dimensional analysis to get the numbers in the correct units. The ideal gas law is much pickier about that than the other ones are.